Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about science and math. And today we're doing part 3 of the notes on bonding. So get out your notes. Let me put it on draw. More fun sound effects. Let's make it a better color. I like pink. Okay, so we see where we ended last time. We did like carbon monoxide, right? Did we got to that? Yes. Okay. So we stopped with covalent properties, and I'm not going to tell them to you. You're going to discover them yourself in lab on Wednesday. So that'll be the last thing we do for this unit. You'll be doing a little lab where you will be telling the difference between covalent and ionic properties, and then that will be on the test. So like I'll have a bunch of properties listed, and like A will be covalent and B will be ionic, or unless you have the other test, that's the other way. And it'll be things like crystalline structure, low melting point, high melting point, things like that. And it's just real quick, A or B, but you have to know which is which, and you'll discover that on Wednesday. Okay? So test Thursday, Friday is a teacher work day, no work, because teacher work days y'all are supposed to have off. It's not supposed to be a digital day. All right, so the last little bit we're going to learn here is we're going to talk about the names of acids. We know about how to name ionic compounds and covalent compounds, but what about acids? Now, there is more to it than what I'm going to tell you right now, and I'm going to assign you a video to watch so that you understand it better. So that's going to be a little bit of flipped classroom. Okay, so how you name them basically is it's hydrogen plus the anion plus ic plus acid. So because acids start with hydrogens, okay? They'll either have one or two hydrogens, and they start with they start with hydrogen. So you start and you say, so like this starts with hydrogen. So we say hydro for the hydrogen. Then you say the anion, and the anion is chlorine. Do you see that? But we don't say hydrochlorine, we just say the root, so it's hydrochlor. So, and then the ending normally is ic, and then the word acid. So there's hydrochloric, there's hydrofluoric, there's all kinds of acids like that. Now there are some other ones like sulfuric acid that doesn't start with the hydro, and also there are acids based on polyatomic ions, and those are a little different, and that's what you're going to learn in the video. Regular chem doesn't have to learn this at all. This is part of your differentiation. So if you're watching the video, this is the honors class for regular who are watching the video, because I'm only going to tape it once. You don't have to, you won't have this extra video. This is enough for you. Okay? All right. Now there's more there. I wrote it down here. There's more rules about polyatomic. We will learn it in a video assignment. Unless you're regular chem, then you don't have to learn it. Okay, other bonds. So we talked about that metals are hippies, and that when they bond to other metals, they just let their little electrons run wild and free, and they share the electrons. And remember, sharing electrons means that it's a bond. Covalent bonds are shared electrons. So this is metal with metal. Now, so these are our hippies letting their little electrons run wild and free wherever they want. And we did this when we did our penny lab, where we took the copper pennies and we plated them with zinc, and then we heated them so it became brass. And those were just metals bonding to metals, letting their little electrons run wherever they want to. But then remember, we said that the hippies can settle down. After Charles Manson, the hippie communes all broke up, and most of those hippies just went around, got married, had kids, had normal little lives, okay? So those are our metals that we were doing last time, where they can actually become ionic and have ionic bonds. So that was where we learned like that silver always has a charge of 1, zinc 2, cadmium 2. Remember how you wrote that on your periodic table. So they can become ionic, and remember that we talked about this, especially the ancient metals can have more than one oxidation state or more than one charge, and we learned how to figure that out last time. Everybody kind of remember that? Okay, good. You're doing good. Okay, so metal properties, we're going to go ahead and list those because it's pretty easy. How do you know if something is a metal? What is it like? Shiny. Very good. They're shiny. Okay. Now, a lot of people say hard, but some metals are actually pretty soft. If you look at the periodic table, we don't think of it as a metal because we usually think of it as an ion, but calcium is a metal. And sodium is a metal. And if you have a piece of it, all uncombined, not sodium and salt, not calcium and milk, but just uncombined, they look like kind of like silver, sort of a dull silver, more like aluminum. They come like in a little block, and they're so soft you can squish them like Play-Doh. They're kind of like Play-Doh-y. So they're not all metals are hard, so don't get that confused. Just the ones that we find uncombined in nature from the middle of the periodic table, those are pretty hard. So then what's another property of metals besides shiny? Got any other ideas? You've learned this before. What?
Could you say solid, even though it's not hard?
Well, what about mercury there? Mercury's a metal. What, according to our periodic table, what state of matter is it? Liquid. So we can't say that. What about what we have it in this room in wires? Why do we have it in wires in this room? What do we want it to do? Conduct electricity. So metals are good conductors. And what do they conduct? They conduct heat and electricity. So there's my one ring to rule them all. Okay. Now, there are other forces that are called bonds that aren't real bonds, okay? They're real important. We like them a lot. There would be no life on this planet without them, but they're not really bonds. For something to be a real bond, you have to transfer or share electrons. Everybody got that in your head? All right, but there are other things that are called bonds that are really called intermolecular forces. So they're not real bond, and they're caused by intermolecular forces. They're caused by intermolecular forces. For example, I'm going to shut this because physics is out in the hall. See, you want to take physics next year, you get to go in the hall and play. Throw balls up and down the hall. Ride on little carts up and down the hall. They ride on those things that people use to change their oil, that you lay on. They just ride on them up and down the hall. I don't know what the lab is, but it looks very fun. Okay, because I haven't taught physics at this school. I've taught it many, many times, but not here. Okay, so a really, really important one is called hydrogen bonds. It's not really bonds, but it's so important it's called that. Hydrogen bonds. And it comes from hydrogen is very low electronegativity. Hydrogen is a wimp. It does not have the ability to hold electrons to itself. So it always ends up having its electron. It'll be in a covalent bond relationship, but whoever it's in the bond with, unless it's another hydrogen, will end up taking the electron more, and hydrogen ends up with a partial positive charge. Remember how we learned about that? We learned that Greek lowercase delta that means partial charge. So this is a real big example. This is water, okay? So it's hydrogen bonds, but you can put little quote marks, air quotes around that, meaning it's called bonds, but it's not really. So because of this, water has got oxygen, and then it's got the hydrogen. The water is partially negative, because it is more electronegative. So it has the partial negative charge the hydrogens are partially positive. And how you write it usually, instead of writing one on each one, you just put the partial positive right there. Sometimes this is shown by an arrow, these things, these charges. And how you do the arrow is you go from the positive to the negative. And I always remember that because you can sort of make that positive look like an arrow tail. So sometimes there'll just be a big arrow like that, showing that that is the positive side and that's the negative side. So this partial positive. Now, so water is really important, and water is needed for life. So whenever we are out in space looking at other planets, seeing if they could possibly have life on them, we always look for water. So why is water so special? It's a polar molecule, meaning it has ends, just like our Earth has ends to it. It's got the polar ice caps. There's our Earth. Didn't I do a good job drawing it? Woo, we'll draw some continents there. I'll color the water blue. That'll make it look more earthy. Oh, it's looking so earthy right there. Okay, so just like how the Earth has the ends, the North Pole and the South Pole, this water molecule has a positive end and a negative end. Let's scroll. Okay, so this property, having this positive and negative end, based on its polarity, that's what it's called. I want you to sort of hear that vocabulary. Results in many things life depends on. One is trees. If water was not polar, trees could not drink. I don't know if you've noticed this or not, but trees do not have a heart. They have no circulatory system. You've all had biology. You should have learned this by now. But yet, big, tall trees can get water out of the ground and bring it all the way up to the leaves. Anybody know how it does that? It's something called capillary action. And it's because water is so sticky, it can crawl up the sides of a very thin tube all by itself. We see this when we learned how to read the graduated cylinder. Remember I showed you that in the graduated cylinder, the water curves, but we read it from the bottom of the curve, and that curve is called the meniscus. Well, if the tube is small enough, it'll curve more and more and more until it'll just suck up. Isn't that cool? It'll just suck itself up the tube. And that's how like those great redwoods in the redwood forest can suck water all the way up into their leaves as capillary action. You might have seen it before. If you've ever had to have your finger pricked at the doctor and it hurts, and you know Elf, remember when he had it done in Elf, they squeeze it and then they've got this little bubble of blood on your finger, and then they hold something up and they touch it to it and the blood goes zoop up into it. That's by capillary action. There is not some little motor in that thing. But when they touch that to your finger, the blood gets sucked up. Have you seen it before? And that's why it's capillary action. Any questions about that? Okay, and if there were no trees, would we have life on this planet? No, because they make the oxygen all of us animals need to breathe, right? And they make all the food. Not just trees, but all plants. That's how they get their water. But trees are the ones that's amazing because they're so tall. So trees can drink based on this. We'll call it drink. Okay? Another big important thing about water is that there would be no life on this planet without it, is it's called the universal solvent. I mean, things dissolve in it really well. If things didn't dissolve in it really well, then there would be no life on this planet. Fish couldn't breathe. The oceans couldn't breathe. Fish do not breathe the O in H2O. They breathe dissolved oxygen just like you do, but just through their gills. Their gills are specially designed to get, and if the sea had no life in it, if it didn't have dissolved oxygen, will we have life on this planet? No, no life on the planet. The ecosystem, you learned about this. It's all dependent. And in particular, the seas are what are the big life generator for our planet. That's all of those organisms that are part of the food chain. Also, all the aquatic plants producing oxygen. There would be no life without the seas. Okay? It's also very important in our bodies. You are mostly IES. You are mostly water. You're a big percent of you is water. And how that works is, all of your food and everything that you take in, your air, it all ends up being dissolved in your fluids, going throughout. It's bound, but it's dissolved in your circulatory system and all of the transport. Remember when you learned about active and passive cell transport? Remember osmosis? You remember all that from biology? All of that works because of the polarity of water. No bio functions without water. You are a water-based life form. Carbon and water. Those are the two things that you have to have for life. So this is another huge one. Water is more dense than ice. Okay, now that's a big deal. It's the polarity of water that makes water more dense than ice. Most elements on the periodic table, most compounds, the solid is the most dense, the liquid is second dense, and gas is the least dense. Does that make sense? But with water, it's the other way around. Water is the most dense, then ice, then water vapor. The reason why is because water is polar. Because water has this polar shape, when it freezes, it makes these little hexagonal rings as the positives and negatives have to line up correctly. And it makes it where there's these little air pockets with, here's the water molecules all around, and there'll be a little hexagonal pocket in the middle. It's why snowflakes are always based on 6. Ice crystals always have 6 to them. If there was not these little air pockets in the ice, then ice, like all the other compounds almost, would be more dense, would have no life on this planet. Why is that one fact make it why we have to have, would that prevent life if it didn't do this? Anybody can figure it out? Yes, Divine. Yes, why? Why would that be bad?
Because that means that icebergs and stuff would sink and it would flood the earth.
Very close. Almost got it. Okay. It's immediately thought the right place. It wouldn't be a tragedy if we put ice in our Coca-Cola and it sunk to the bottom. No, it has to do with the bodies of water. You're exactly right. Okay, so you've got this lake, and it has fish in it. If the ice was most dense, as it got cold through the winter, the ice would sink and then go to the bottom. And then more ice would sink and go to the bottom. And then more ice would sink and go to the bottom until it totally froze. Then all the fish would be on top flapping and they would die. They would not make it through the winter. But instead, water is most dense at 4 degrees Celsius. So as it's starting to get cold and freeze, the cold water sinks, the 4 degrees Celsius water. But then as it gets even colder, it starts to freeze and it floats to the top of the body of water, like the iceberg. And it floats on top. All the fish are down here where it's all liquid still. Up top, these air pockets are in the ice making insulation. So the water stays perfectly designed for life through the winter. The fish are all there all winter long. You can even go ice fishing. And then there they are in the spring, ready to be alive and to continue life. Isn't that interesting? No life on this planet if ice didn't float. Okay, so this is important for bodies of water. They would freeze and all the fish would die. This controls the temperature of the water. Oh, no. So this is a different point. That does control the temperature. Okay, so there's another reason. It has to do with temperature. If we did not have water on our earth, we would all die. Like tomorrow, if suddenly the oceans evaporated. Do you know why? What?
It'd be too hot here.
It would be too hot and too cold. Okay, so water, because of it having this shape, is very, very sticky. It sticks to itself really hard, and because it does that, it resists change. It resists change. And in particular, it resists change in temperature. So all day long, like how Lori said, the sun shines on the earth. But we don't burn up and die. We don't get so hot, our planet can't sustain life like all the other planets because we're covered with water. And that water has a cooling effect because water is very resistant to temperature changes. We're going to do a whole unit on temperature called, and this property called specific heat. Water has a high specific heat because it has this polar shape. It sticks together so hard that even though the sun shines on it all day long, it doesn't heat up that much. It just absorbs the heat and absorbs the heat and absorbs the heat, but it doesn't change its temperature very much. It absorbs the energy, but its temperature doesn't go up. Then at night, our planet turns away from the sun, and on other planets at night, it gets too cold to support life. Other planets in the day are too hot, and at night are too cold. But our planet, perfect for life, turns around, and at night, when we don't have the sun anymore, and we would become so cold that we couldn't live, the water gives that heat back out, and we have perfect temperatures for life. Isn't that amazing? It's shocking and exciting how perfect it all is. But yeah, so when they're out in space looking for other planets that have life or that where we could go live and colonize.
Sorry, could you say that again? Sorry, I'm having trouble.
I don't know why my watch wanted to talk about this. Probably amazed too at water. Anyway, they're always looking for planets like ours that are covered at least, 2/3 with water. If they're not covered 2/3 with water, they are not going to be able to support life. That's pretty shocking, isn't it? So there might be like some sort of microscopic, there might be a bacteria there, there might be an amoeba there, but there is not going to be a man there. Not without water. Not without water. Okay, so this controls the temperature of the Earth. Okay, Earth is a. I don't have my whole thing. I have to remember what it was. Okay, Earth is a water planet that controls our temperature. So the other problem is it's mostly salt water, though, and we need to drink fresh water. So this causes a worldwide problem that we need fresh water for life. To drink, to stay alive, we have to drink fresh water. Salty water won't work. In my last semester, my honors classes did a STEM unit about water purification. We took some time and did a STEM unit. If we do it in this class, we're not going to do it now. We'll do it later because I want to we'll go back and do it possibly when we go for the heat chapter. We might look at that then. Okay, so that's the notes. Any questions? Are you all inspired about water now? Did it make you thirsty? Did you want to drink some? All right, like, share, subscribe. Science is great.